Hello and welcome everyone to another CAA webinar. I know we're going to have a great time today, this morning, this afternoon, this evening, wherever you may be in the world. Today, we are going to be unveiling the CAA's climate tool that we have been working with the SOA in developing. But before we go into the session, I would like to thank those who attended our last webinar held on October 24th. That webinar is now on our YouTube page. You will see the link to that YouTube in the chat. Also, I'd like to remind you of our CAA conference that begins on November 29th and runs till December 1. This year, we will be in Trinidad. If you can't join us in person, you can join us virtually. Registration closes this Friday on November 24th. The link will be shared in the chat. And I'd like to give a very special welcome to our presenter for today, Patrick Wiese. Patrick is an actuary in the Society of Actuaries Research Institute, where he builds models and virtualization tools covering a diverse range of areas, including climate change analysis, mortality improvement trends, and retirement income security. Patrick is a member of the research team that developed the Actuaries Climate Index, an online tool for monitoring long-run trends in frequency of severe weather in North America. In addition, Patrick is a co-author of the SOA's Actuarial Weather Extremes Report, which provides statistical summaries of extreme weather events. Prior to joining the SOA in 2012, Patrick developed long-range forecasting models of social security and retirement systems in low and middle-income countries for projects funded by the World Bank and the Asian Development Bank. Before Patrick begins, I would just like to inform you that this webinar is being recorded and will be uploaded to the CAA's webpage, YouTube page, and/or ActiveView. This may include questions in the Q&A and responses, as well as chat responses. By registering for this webinar and attending this session, you hereby give the CAA permission to use any text, photographs, or videos taken during this virtual session. I now hand over to Patrick.
Thank you very much, Rohan. And thank you to the CAA for inviting me here today. I'm going to go ahead and share my screen. And we'll begin with a PowerPoint set of slides to give some background information. So I'm going to show today a tool that that we've been using, the SOA together with the a working group that's focused on studying weather trends in the Caribbean region using ERA5 data. And I'm going to explain more in a bit about this really fantastic data set, ERA5. This working group was formed last summer. The goal of the group is to study climate change in the Caribbean region with an emphasis on identifying trends that would be of interest to actuaries. The SOA is participating in this. I'm a member of the working group, and to facilitate our analysis, we've developed an Excel VBA toolkit that makes it easy to study the ERA5 data, to examine trends, to visualize the data. The toolkit is really a means to an end. We're using this toolkit to develop ideas that can later feed into the development of a climate index for the Caribbean. We'll start off, I think we should talk about data requirements. what is needed to study climate change. We're going to look at two different data sources, GHCN station data and ERA5 reanalysis data. These are two well-known data sets that are both very useful, but they have different strengths and weaknesses. We're going to compare these two data sources for a location in Puerto Rico. And then lastly, we'll do a demo of the tool that the SOA has developed to support this effort. This tool is loaded with data, ERA5 data for the Caribbean, but it could be used to analyze data for any part of the world. For climate change analysis, it's important to have a long time series of data. 5 or 10 years of data, you will not get a lot of mileage out of a data record that is that short. You really need several decades, 40 or more years. You're getting to a point where good analysis is possible. The data obviously has to cover the region of interest, in this case, the Caribbean. It should include key variables, key weather variables, temperature, precipitation, wind, sea level is very important in the Caribbean. And it should have units of time that are small enough, short enough, that we can examine extreme events. There's a lot of weather data sets that provide data in monthly time increments. So you might have monthly precipitation. Those are interesting data sets, but they aren't generally helpful for examining extreme events. If it rains 10 inches in a particular month, it matters whether those 10 inches came on a single day or a single set of days, short period, or whether they were spread out across the whole month. So I think daily data is really the ideal time unit, or even hourly data. There's various varieties of weather data. Two of the primary types of weather data are direct observations and reanalysis data. GHCN, the Global Historical Climatology Network data set, this is an example of station data. This is data that's collected directly by land-based weather stations. The GHCN data set has data from more than 100,000 weather stations worldwide. But these stations are not distributed evenly around the planet. They are concentrated in certain areas, and they are less frequently found in other data. So that's one challenge in using the GHCN data set. Reanalysis data is quite different from station data. Reanalysis data uses information data gathered from many different sources. So land-based stations, ships, weather balloons, satellites. Data from all these sources play a role in the development of reanalysis data. You can think of reanalysis as kind of like filling in missing pieces of a jigsaw puzzle. So you start off with data gathered from various locations around the planet, but there's information that is missing. We don't have weather stations everywhere. And reanalysis uses weather models to fill in the pieces. So the end result is a data set that is spatially complete and complete across time. The ERA5 data set is an example of this. 5 stands for fifth generation RA reanalysis, and the E indicates that the data is from the European Center for Medium Range Weather Forecasts. This is a data set that we are using frequently for this working group, and we've also been studying it quite a lot for the North American ACI. We've become increasingly interested in ERA5 because because it offers spatially and temporally complete data. That's one of the key reasons that the data is of interest to us. GHCN stations, this is it's a critical data set. It actually feeds into most reanalysis data sets as an input. And you can certainly try to use the GHCN data as the basis for constructing a climate index, but it's challenging because many of the weather stations have data for only a short time period. So while there are 100,000, more than 100,000 stations in this data set, a small percentage of them only have data across a lengthy period. So you can see on this map, we have 138 stations in the Caribbean that have at least some temperature data, but there are only 9 that have lengthy data histories. And I defined lengthy in this case as data that is 90% complete back to 1980. And so unfortunately, you see that most of the map here is blank. That is not unusual. The Caribbean is not alone in this situation. I think most of the world, if we were to do an identical analysis, we'd find a lot of blank spots in different regions. So the question is then, what can we do? What data set should we use to build a climate index for the Caribbean? ERA5 is one option. It provides data every 0.25 degrees of latitude and longitude. So on this map, every one of these small dots represents a location for which ERA5 data is available. The data is available over both land and sea, so that's another advantage, particularly in the case of the Caribbean, where we have a lot of we have islands, but we have a lot of sea that could potentially be of interest to us as well. There's a parallel data set called ERA5 land. It's gridded at 0.10 degrees, so it's a finer grid. The dots, if we were to map this, the dots would be squished much closer together. And it's also it's a good data source, but it provides data solely over land. ERA5 offers a lot of weather variables. It's not just air temperature and precipitation. There's dozens of different variables. I've listed a few of them here. Air pressure, wind speed, soil moisture, sea surface temperature, and sea surface height. So there's a lot gathered together in one place, which is another aspect of this data set that makes it very, very convenient to use. A natural question is the data reliable? I mean, it seems at first it's a little bit too good to be true that we have all of this data for the whole world, dating all the way back to 1940. This is, I think, the right question to ask for any any project like this. You've got to be concerned about the quality of the data. This is a very tricky question to answer. A lot of researchers study this. The results vary from one geographic region to another, and from one weather metric to another. Studies are usually regional rather than global. So if you do a Google search, search for ERA5 data quality, you'll see dozens of different papers each aimed at a different location and a different weather variable. I did a search for the Caribbean. I think there's been a couple small studies, but I did not find anything comprehensive that evaluated ERA5. I think this leaves an interesting opening for a research team that wants to dig into this. I think it's a project unto itself. We're not tackling it at this time. We're mainly focused on using the data, but of course we do need to circle back and study the data more closely and see how it measures up against the land-based station data that we do have at our disposal. Comparing ERA5 against land-based stations, it can be a little tricky because stations and grid points seldom fall at exactly the same location, and they seldom are at exactly the same elevation. And elevation can be very important. If you're comparing a land-based station that is, say, on the side of a mountain, and the nearest ERA5 grid point is down at the base of that mountain, there's then an elevation difference that may not make the comparison apples and oranges, but it may complicate your effort to make a comparison. I did a very simple comparison of ERA5 versus GHCN. I focused on one weather station located in San Juan. I focused on temperature. This station, it has temperature data back to, I think, 1953, so it has a very long history. It's located at the airport, and this little map shows the 4 closest ERA5 grid points. You can see that they're close, but they're not exactly coinciding with the airport. Points 1 and 2 are actually in the sea, so that that's one thing that makes this not quite apples to apples. And points 3 and 4 are set a little inland and at a slight elevation relative to the airport. So we don't really have a perfect apples to apples comparison here in terms of latitude, longitude, and elevation, but it's useful to go through this exercise. The upper table shows correlation coefficients, GHCN versus each of these 4 points. This is for daily high temperature. The coefficients are calculated using 2022 data, and you can see that all the coefficients or nearly all the coefficients are above 90%. I think that's a good sign. That suggests a pretty strong correspondence between the data. And then the lower matrix focuses on daily low temperature, and again we have some pretty respectable correlation coefficients. So this is encouraging news. We again look at the same 4 grid points compared against the data for the GHCN data at San Juan Airport. Here we're looking at annual average temperatures, and we see that these time series are the troughs and the peaks of each time series are matching up well. So they kind of show parallel movements with each other. That's encouraging. But of course, we see differences here. We see that the airport, the black line at the top, is showing a higher temperature, and the ERA5 grid points are showing lower temperatures. Now, that one possible interpretation of this is that the airport is simply at a warmer location. Two of the grid points, the ERA5 grid points, are offshore, and the other two are set back in the foothills. So it's quite possible that there's no discouraging news here, that everything fits together quite neatly. When using the ERA5 data for our analysis, both in the Caribbean and for North America, what the working groups have done is to convert the data, the raw data, from hourly time units to daily time units. We do this because if you don't make the conversion, you are left wrestling with really very large data sets that can be in excess of 100 gigabytes. And it just complicates one's analysis, because any tabulation programs that you run on these files may take a long time to run to completion. So we convert the data as a first step. We convert it to daily format. For temperature, for each 24-hour period, we take the daily maximum. That goes into one set of files, daily files. And then we also take the daily minimum temperature. So that leaves us with two parallel sets of daily data files that are much easier to work with. They're 1/24th the original data size. And we really don't sacrifice much, because for the most part, the daily data is perfectly adequate for any kind of analysis that we wish to do. We could have also computed daily average temperature and make a separate set of files for that. We may do that at some point, but for now, the maximum and the minimum temperature has been sufficient. And then the daily data files we feed into our analytical tool, and that's the tool that I'm going to demonstrate for you today. The tool has an Excel surface, so all of you would feel familiar, like you're in familiar territory if you're using this tool. And all of the task of reading the data and analyzing the data is performed by VBA. The data itself it's outside of Excel. It's sitting in CSV files that you can keep on your laptop or desktop. We had to set it up like that because even in daily format, these files would be so large. If we were to store them in Excel, the Excel file would basically be unusable. And now let's go ahead and demo the tool. Let me switch over here. So the tool it has a series of separate tabs. Each of these tabs has a different function. There are tabs 4 through 9 are the tabs that actually perform some sort of exercise with the data, calculating exceedance curves.
Sorry, Patrick.
Yeah.
Have you switched over to the Excel? We're not seeing the Excel as yet.
Oh, you're not seeing the Excel.
Okay, stop sharing and then reshare.
Yeah, let me try this again. Here we go. And let's get over to the Excel. Yeah, thank you, Rohan.
Okay, seeing it now.
Okay. So the file has a series of tabs. Each tab has a different function. Tab 1, you have to let Excel know where the data is stored on your laptop or desktop. So I have the data. I have the daily maximum files stored in one location, the daily minimum files stored in another. There's a separate CSV file, comma separated file, for each ERA grid point. And I'll get to more about that in a moment. The data that we've set up for the Caribbean region, it's about 3 gigabytes. 3 gigabytes for the daily maximums and 3 gigabytes for the daily minimums. So that this data will easily fit on somebody's laptop or desktop. 3 gigs may sound like a lot, but for weather data, it's really very compact. Some weather data sets are 100 or 1,000 times larger. This map shows what data we have placed in this example. Keep in mind that ERA5 provides coverage for the entire world. So in theory, you could set up this tool to work for any location. In practice, I think it's a little easier since I'm doing this work on my laptop and others in the working group are working on their laptop or desktop. It's helpful to narrow down the ERA5 data set before you launch into your analysis, so the data is a little smaller, so it's not gobbling up all the space on your hard drive. So I've this inner box is really where I'm focusing, this dark blue box. Within this box, I have captured every single ERA5 grid point, every 0.25 degrees of latitude and longitude. Outside of this box, you'll see there's an outer rectangle that extends into the southern US and also extends into South America. I've included this outer box, but at a lower density of points. The outer box contains only those grid points at every 1 degree of latitude and longitude, as opposed to every 0.25 degrees. I think it's interesting to include these other points just because they offer us a comparison against different types of climate. But we certainly don't need a lot of density. We don't need every point. So that's why I've thinned out the data in this outer square. And now we can move on to the tool itself, the working part of the tool that transforms the data into graphs and results that the working group is studying. The idea here is to offer different ways to examine trends in the data, kind of a menu of different concepts that the working group can examine, and hopefully will lead us towards selecting metrics that we think will be optimal for the Caribbean Climate Index. So this tool is a means to an end. It's a means to do research. It's not necessarily the end in itself. Let's start off by, I'm going to load in, let's pick a location. Why don't we look at, let's look at Jamaica, Kingston, and I'm going to load in the latitude and longitude into the spreadsheet. I may have already done this. Yeah. So latitude 18 degrees north, longitude 76.75 degrees west. This location doesn't coincide exactly with Kingstown, but it's the closest ERA5 grid point to that location. It typically, the gap, if you're looking at a particular city, the distance to the nearest ERA5 grid point will be less than 10 miles or 16 kilometers. So you can get pretty darn close to the location of interest. Let's graph this data for 3 different time periods. Let's look at 1940 to 1979, 1980 to 1999. And then finally, the year 2000 to year 2022, we're going to look at all observations, all daily observations from January through December. So the whole year. If we wanted, we could narrow this. I could, if I were to enter this set of parameters, we would just be looking at the month of July. So this gives us some flexibility. If we want to do a seasonal analysis or a monthly analysis, we can. Now we press generate curves. The graph redraws itself. And we see that these curves are, they're not identical. They're each a little bit different. And they're reflecting shifts in climate that have taken place over the last 80 years. This vertical axis is a probability from 0 to 100. The horizontal axis is daily high temperature. And let's just pick a particular point here. Let's look at 28 Celsius. If we move upwards, we'll see that this first curve shows that from 1940 to 1979, there was a 28.8% chance of the daily high temperature exceeding 28 Celsius. We then shift upwards. We're now going to the next time period. This is 1980 to 1999. And that probability is now increased to 39%. And then we can shift up a little further to the most recent time period, 2000 to 2022. And now we are up to 43.8%. So we're seeing a shift in temperatures. If we want, let's say we're interested in the upper end of this distribution, I can redraw the graph. I can enter a temperature range here. I'm going to leave these parameters as they are. We're going to focus on the range from 26 Celsius to 31 Celsius. I redraw the graph. And whoops, let me change that, redraw the graph. And this makes it a little easier for us to focus in on the upper end of this range. Nothing changes in terms of the data. It's the same data set. We're just looking at the upper portion of it. We can go one step further. I can set this parameter to yes, and I can redraw. And when I redraw, the first curve here for 1940 through 1979, that will serve as a benchmark against which the other curves are drawn. So what the graph will do is draw the difference between curves 2 and 3 relative to curve 1. So we can think of curve 1 as a reference period, and the other two curves will be expressed relative to that period. So I redraw, and now the numbers become quite easy to interpret. We see that for the period from 1980 through 1999, we have an 8 to 10% increase in the probability of experiencing a daytime high temperature above 26, 27, 28 degrees Celsius. We go out closer to the present time or all the way up to the present time. This upper curve, we're looking at the last 22 years from 2000 onward. And we can see the probability has shifted up further. And so this is one way that this tool can take the data and make the data easy for us to see underlying trends that might be of interest to actuaries. Let's do one more exercise here. let's remove these curves 2 and 3. Let's look at the entire time period, 1940 to 2022. I should add that 2022 it's the last year that I've included in this data set, but ERA5 runs all the way up to the present with a very short time lag, with a lag of only 5 days. So there is no reason, if somebody's interested in the latest data from the last month, that data is available. For this exercise, I felt that we could just work in complete years rather than including 2023 as a partial year. So that's why the data is truncated in 2022. Let's compare 2 locations against each other. I'm going to enter Washington, D.C., where I'm located, 39 degrees north, 77 degrees west, and we're comparing that against Kingstown. We redraw, and here we're not looking at climate change. We're simply studying climate, and you can see that for Washington, D.C., we have a much broader range of daytime high temperatures, and that, of course, is because the further we move away from the equator, the more dramatic is the effect of the seasons. And conversely, the closer we are to the equator, the tighter, the less volatile will be seasonal impacts, at least with respect to temperature. So this is quite interesting. You know, simply for studying climate rather than climate change, this can be an interesting tool. Let's just see what happens if we just zero in on the month of July. That should remove a lot of the seasonal change for Washington, D.C., but we're still going to see differences. We still see that Washington, D.C. has a much broader range of temperatures. So this is one of the tools that one of the tools that we have inside of this spreadsheet. I think we have time to show one more of the spreadsheet's tabs. Let's look at tab 5. And this tab fits a linear regression to the time series of data. It divides the data into blocks of 1 year each. So we could go all the way back to 1940 if we wished. I'm going to run this example from 1960 onwards. And for 1960, for 1961, for 1962, and so on, for each of those years, the tool, in this example, it computes the average temperature, and then it's going to fit a regression to that time series of annual averages. We don't have to use the average. We can examine something else if we wish. We could look at, if we set this to 100, we'll be looking at a time series of maximum temperatures, the maximum temperature observed across the course of a year. If we set this to 0, we'd be looking at the minimum. This is actually a common technique used by some, for example, by hydrologists. Sometimes will examine extreme precipitation events using a technique called block maxima, where the block means blocks of time, and for each block of time, they're plucking out the maximum, and they work with that time series. In this case, let's use the average. We're again focusing on, let's make sure we've got the right data point. Let's get Kingston. We have it, and then we run the tool. It generates a set of results, and I'm gonna jump straight to the graphical part of this. We can graph our results here. I'm going to plot the time series of data, and I'm going to also plot the linear trend that we fitted using the regression. We press graph, and here we have our results. So we have the actual time series of average annual temperatures, and then through that time series, we fitted a linear trend, and you can see this upward movement of temperatures is quite visible here. Now, temperatures don't always move linearly. Probably they really never do. So we can also plot moving averages. Let's plot a 10-year trailing moving average. Let's remove the linear trend. And now we have the same underlying data, but in addition, we have a 10-year moving 10-year trailing moving average. We can see that there are a couple periods here where that moving average is heading upwards at a pretty steep rate. There's a level period and then another upward movement. Let's do one last exercise with this tool. Let's look at why don't we look at the maximum? Let's look at the maximum and the minimum, and let's do it at the same time. So we run both of these. We now have two time series, one of annual maximums, the other of annual minimums. There's some regression statistics here. We have the slopes. This is a confidence interval of slopes. So the low end of the confidence interval, the high end, this is the best estimate. This is the slope expressed as degrees Celsius increase per year. So the expected annual temperature is going up, the maximum temperature and the minimum temperature going up at about the same rate in this example. Let's go ahead and plot both of these time series. It's a bit tricky to see the slope with both of these series on here, but they're kind of moving together. Let's see if we have, we have 14 minutes left. I want to leave a little bit of time for questions. I think we can do very quickly one more tab. So tab 6, the idea here is that we are replicating metrics that we currently use in the North American ACI. We are replicating those metrics using ERA5 data. I'm gonna just run this, and then I'll explain what we're looking at after I run it. So here we go. Oops. Let's graph the results. This is quite a volatile time series. It's volatile because what we're doing here, we set up a reference period. In this case, the reference period is 1961 to 1990. And from that reference period, we extract the 90th percentile of daily high temperatures. And then going as we move through time, for each year in this analysis, we count the percentage of days that exceed that 90th percentile. The idea being that, actuaries, while we are interested in averages, average temperature or average precipitation, we are particularly interested in the tails of the distributions. So this is one way of studying the tails. Let's just look at one observation here, 2010. We see that the resulting number is about 20%. And this means that in the year 2010, 20% of daily observations exceeded the 90 percentile threshold obtained from the reference period. Yeah, that may be a little confusing to think about, but if you study the website for the North American ACI or the Australian ACI, they're both constructed on similar principles. Those websites will probably do a better job of describing this type of metric than I just did. So to finish up, this is really a tool. It's a means to an end. We wanted to create something that would enable us to study this data easily and to generate ideas that we think will be useful for a Caribbean climate index. We're in the middle of our research. We have a ways to go. And hopefully, a bit down the road, we will have a finished Caribbean index that we can share with anybody. And so I'm going to stop there, and happy to. I'm going to stop the screen sharing. I'm happy to take any questions that we have from the audience.
All right, thank you very, very much, Patrick. Yes, we do have a few questions. The first one is, in your charts on exceedance probability by daily high temperatures, does it surprise you that at higher temperatures, the data points are closer together? Wouldn't we expect greater variation at higher temperatures, meaning that extreme temperatures are getting higher?
Now let's go back to, let's open it up again. And let's go back to the exceedance curves. And let's redraw. I'm assuming my main example generated that question. So 19. Rowan, would you mind? I want to make sure I understood the question. So could you repeat it one additional time?
Sure, no problem. In your charts on exceedance probability by daily high temperatures, does it surprise you that at higher temperatures, the data points are closer together? Wouldn't we expect greater variation at higher temperatures, meaning that extreme temperatures are getting higher?
Yeah, so I think we redraw this as what we're getting at. I think the question is why, to restate it a little bit in graphical terms, why do we have a big hump here and much smaller values here? It's a good question. I think that the graph may have to look like this at extremely high temperatures, because we reach a point at the upper end of the temperature distribution where despite climate change, we're just not experiencing that many days that exceed 31 degrees Celsius. Maybe if you were to look at this in terms of ratios of exceedance probabilities, so we computed the ratio of these two lines, perhaps that might line up with what the audience member is suggesting here. But I don't see anything in here that strikes me as counterintuitive. We're seeing more and more days above 28, 29, 30 degrees Celsius. Then the curve slopes down. Climate change is affecting all points on this distribution, but there just aren't that many points up here, in this case at 31 degrees Celsius, which is, good news. We're hoping that that climate change won't lead to really a catastrophic increase at the high end of the distribution. I'm not sure how well I answered that, but I did my best.
Well, the attendee, you could indicate back in the question box if that answers your question. But I'll move on to a second question. All right, so you've been presenting on temperature, and the question is, could there be similar stats shown for sea level, rising sea level?
Yeah. Well, I think this analysis would fit very neatly with precipitation for sure. With this tool, in fact, I'm working on a tool that it's going to be very similar, that handles precipitation data. Sea level data, I think we will have a tool, certainly, whether it has the same metrics, I'm not sure yet. The sea level data from ERA5 is in monthly time intervals, not daily. So that's one difference. You don't have, we don't have daily data to work with. So that's, a potential avenue of exploration that we don't have. And then in regard to the monthly data, we haven't yet begun running our fingers through it, but I think we're going to see muted changes from month to month, with a very clear upward trend. So the nature of the data is a bit different. We may come up with different graphs and metrics for visualizing that data. We'll have to see. But it's good that ERA5 offers this as data, and we'll dig into it pretty soon, I think.
Okay. All right, and another question, does ERA5 include humidity data that can be incorporated into the tool?
I think it does. It has dozens of different metrics, and I'm 97% sure it has humidity data. An easy way to find out is to Google Copernicus Data Store, which is the portal through which ERA5 offers its data. And once you're there, type in ERA5 single level. That's the data we're using. That refers to whether we're looking at data just for the Earth's surface or whether we're looking at different levels of the atmosphere. We are interested in the Earth's surface, so we use the single level data. And there'll be a menu there that lists all the variables. And almost certain that humidity is one of those variables.
Okay. And I think this one might be our last question. Do you have plans to make the ERA5 toolkit available to actuaries or to the public?
Well, we're just, we have to see. We're right in the middle of our research, and the tool was created primarily as a means to an end, not an end in itself. But it's possible that some point down the road we'll decide that it makes sense to release the tool or something, a variant of this tool. So you can check in with us, I think, in a few months, and we may have a decision on that issue.
Okay, and I'll try to squeeze in one more. Would there be a trend of apparent increase in temperature because of man-made structures? For example, measuring temperature at the same location over decades as tree cover gives way to more heat, gives cover to more heat radiant structures.
Well, it's probably a question for a climate scientist rather than an actuary, but I'm a user of a user of the data, not the producer of the data, but I would think that the local conditions can matter. So if you have a particular location that was once covered in trees and has now been stripped of trees, it does seem like that could have an impact on the local temperature measurements.
Okay. All right, I just want to say on behalf of the CAA, thank you very much, Patrick, for making yourself available and doing this presentation for us. As the team continues to work on the tool, the climate tool for the Caribbean, we look forward to having the results. And before we go, I just would like to remind everyone of the CAA conference coming up in November, starting next week, Wednesday to Friday, as well as you can go ahead and check out our YouTube page for the last webinar we had, and this webinar will also be shared once it's posted. Thank you very much, everyone, and have a good afternoon.
Thank you.